Hamiltonian. Yeah, this is 0, but not always, not always. But in the easy case, yes. H and H sometimes is not 0. You know? You can have the case which H and H don't complicate, like the angular momentum. Is a vector, but the component of the data, the L and L is not 0. It's not only L, so L maybe is a very elementary example. We have a case that Hamiltonian cannot be communicated at the different times or something. So look at that. We find that dH dt is partial H, partial H. And if Hamiltonian will be really function of the time, not function of the time, so you can set it as 0. So that will be the equation. Before to go forward, I want to remind you one equation from the chapter of the phase space. You remember when we studied the Liouville theorem there. You remember that in the classical ensemble theory, we started our discussions by considering the time evolution of the density function, we call it rho. It was the density of the particle in the phase space. Huh? Yes. How many particles are located in the spatial part of the phase space? I just remind you that you remember we started from here, we take a volume from that, the omega, and we call it this rho is the rho q, and the p is the density function, density of the particle in the phase space, and very formally we write this is a q and this is a p. You remember what was the equation for the evolution of this? d rho dt was, you remember, was rho and h plus partial rho on the t. Yes? Liouville theorem. We proved that by considering the time derivative of the general function of any function of the rho and using the Hamilton equations. I can write this equation another form, yes? Minus h and rho, yes? I can write it. Yes. Now just no any conclusion. Just let me to see if you just compare the classical Liouville theorem this Liouville theorem is very, very fundamental theorem in mathematical physics, not only in statistical physics, in many disciplines. Classical Liouville theorem. Just compare this equation with the equation of the Heisenberg. Don't think this is a rho is the same as here. Just d dt is minus Poisson bracket plus partial, and d dt is IH bar the Dirac plus partial. So what you understand is the partial derivative is the same as here. Just it seems that if you replace it h and every operators to the IH bar Dirac or if you replace it Poisson bracket, it seems that you can pass from the classical Liouville theorem to the quantum mechanics. No, it's not that. Not always. For any operator, you can do that and pass from the classical mechanics to quantum mechanics. But for density operator, you will see that it will be a little bit different. But anyway, this transformation make a possibility for you to think about the density state in classical phase space and some quantum variant of that, quantum version of that, quantum version. And the time evolution of the density function in classical phase space and the time evolution of the quantum version of these operators. That was what I told you at the beginning of the lecture. I say that I want to find the density of the particles in the quantum mechanics. I want to see that what's the analog of that. So we are a little far from to give the statement of the quantum Liouville theorem, but we will see that. I want to give more information about this Heisenberg representation because I will start a little bit more detail about the. I want to little bit start to give the idea of how to writing the how to write the form of the operator rho. So to write the operator rho, you needed to. I told you needed to work about the representations. So, yeah, there is a problem here, and the problem is that to write a quantum version of the statistical physics, you need to write the quantum wave equation for the system with more than one particle, no? Like n particles in distance. So this is actually many problem. Anyway, so we have the edge, and edge satisfied, or you can build an eigenvalue, an eigenfunction equation for this operator, and this operator need to be Hermitian. You know that always is possible to have a set of the basis functions and set of the eigenvalues, and the basis function should build a complete set. I mean, they should be orthogonality. I mean, if you multiply two of the same index, you get one, or if you have the different one, you need to have the zero. This is like the vectors, the normal vectors in the Cartesian coordinate. And the other things is that the energy value should be real number. If you give me a Hamiltonian, a test to see that this Hamiltonian is Hermitian or not is that you find the eigenvalue. By finding the eigenvalue, if the eigenvalue is real number, so you can be sure that the Hamiltonian is Hermitian. If you get some complex number for eigenvalue, it means that the operator was not Hermitian at the beginning. So they are basis function. Basis function like the vector, the Cartesian vector ijk. So you can represent any vector in terms of them. You know that V can be written as Vxi plus Vyj, because there is a curve. So that's working for us like a general vector. So I can write this general vector psi er like sigma Rn phi n. Yes.
Here measurement give us observable quantity in that?
Yes. If you want to measure a quantity in the experiment, you need to label this quantity to the Hermitian operator in the quantum mechanics. So that's the reason that you can measure, for example, the magnetic moment of the electron. You can measure the spectrum lines of the hydrogen atom, or you can measure the intrinsic angular momentum of nucleus, for example, nuclear physics. My starting point will be this equation. You need to focus on this equation. This equation just is like a vector decomposition of the vector over the component, like ij. Instead of the ij, I have phi1, phi2, phi3. So the dimension of my space is infinite dimension, not 3 dimension. It runs from the 0 to infinity. So this is actually sometimes it's finite dimension, like the electron in the magnetic field. You have it just 2 states up and down, flip it up and down. So the Hilbert space for that, it made it just by 2 vectors up and down. So 2 dimensional actually. And the matrix will be 2 times 2. But here you have a lot of like harmonic oscillator. You have many energy levels, so it runs from 0 to infinity, so the Hilbert space, the dimension is infinity. So. Anyway, I want to work a little bit on this equation. So what is An? How I can find the An?
Normalization.
Orthogonality condition. This is the orthogonality condition actually. Orthonormality. Normal condition. Normal because it should be 1 if they are, and orthogonal because if they are not same, so it will give you 0. Orthogonality condition. So I can multiply that to phi m and make integral, of course, dr or dx, how you want it. If I write r, okay, keep it the r at the beginning, r. Okay. And this I can write phi m psi e. Phi m e here. I can write the phi m e. Just the static energy E. You know, psi e r, you remember a few minutes before, was r projected over the state. The state is E. I want to replace this Rm here, just for curiosity. So by substituting Am, what we get? I replace this here, so psi er will be sigma n phi n e phi n. I can write them like a vector to be just more precise. And that I can write like sigma n phi n over the state E, or over the psi er. Anyway, don't be so confused. So psi er or notation of Dirac or not notation is the same. So you get one thing very interesting. Psi er is something multiplied to psi er. So that will be 1. That should be 1. So 1, but which one? Operator 1. So this is called completeness. With this operator 1, you can
the operator of A, it is not the same as expectation, yes? Yeah?
no, expectation means that when you have this, yeah, this is the expectation value of the operator, or quantum average. So this completeness will be my starting point, but I don't do that now. Our starting point to write the rho in quantum mechanics is using the completeness condition. Just I will write one more equation, and I want to finish this now. So there is something here. I told you that phi n should satisfy the autonormality condition. So they should have the length or norm 1, and they should be also orthogonal to each other. So that's very essential. It's very essential to have the orthogonal form of the operator. This 1 is really 1 because, you know, if you multiply 1 to that, I want to see that if this is a really 1, so 1 squared will be 1. So let's just see that, huh? This is the check to be sure that 1 is 1. Otherwise, how can I say this is a 1? And this 1 is operator. Why I call it this operator? Because here there is a free. You can put it something here and make the action from that. Apply that to the anything. So here is free, so it's called operator. It's like operator equation. 1 squared is 1, 1. Okay. So this is like phi n, phi n, phi m, phi m. This is the autonormality condition, phi n and m. Because that's what we suppose that the phi n should be autonomous. So I can write, we have a double sigma here. How you do with that? Only possibility is that n equal to m, otherwise it will be 0. So 2 sigma will be reduced to 1. And this is the operator 1. So this is the real one. And if you continue, you can have it. The higher power of operator 1 is 1. So this is the really operator 1. Don't think that this is a dot product or something like that. There is no, this is a direct product actually. This is a direct product. So another notation for that is that we can write, because you need to know what is this kind of the product is the tensor product or direct product. We don't write this cross, but we need to always remember that here there is something, but we don't write it. This is a cross. It's not the dot. Dot is this. This is dot. Phi and dot. So they are 1 or 0. 1 or 0. This is the cross product or direct product. They call it direct product. Okay, because I think I will stop it now here because. So